In this lecture, we will discuss about the resonance in AC circuits. This lecture will cover the introduction to the resonance in RLC series AC circuits, and resonance in RLC parallel AC circuits. So what is resonance basically? Resonance is a condition actually in which the voltage V and the current I are in phase. So the basic definition is this one. When the voltage, so let us consider an AC circuit, a general AC circuit in which we have an AC source and it is a voltage source, and then we have some load basically. This is some load which is of RLC type, and let us say that capital V is the RMS value of the voltage and capital I is the RMS value of current. So V and I are the RMS values of V and I respectively, where these two are the instantaneous quantities. Now, when these two parameters, that is the voltage and this current of this particular circuit, are in phase, we say that the resonance has occurred in the electric AC circuits. Now, so when we have to draw the phasor diagram of this one, so phasor diagram would be like this. This is the current phasor, and then V, this would be the voltage phasor. So you can see these both are in same phase. So when these two quantities are in phase, so it means that the phase difference that is phi is 0. Now what does it mean? It means that when phi is 0, then the power factor of the AC circuit is cos phi. So it is cos 0 degrees. So it is 1. That is, we call it as unity power factor. So that means from here we can have a new definition of resonance, and that could be resonance is a condition at which the power factor of the given AC circuit is unity. Now, let us come to one more thing. We know that cos phi is also equal to R by Z. Now this we have understood in our previous lectures, that if we take the impedance triangle, for example, So if this is, let us say, O, this is A, and this is, for example, B, and this is angle phi, and we have the various, let us say, parameters here, Z and R and X, where X is the reactance. Now, OB upon OA is nothing but cos phi in this particular triangle OAB. So cos phi is equal to R upon Z. So at resonance, because cos phi is 1, so R by Z is also equal to 1, or Z is equal to R. Now what does it mean? It means that at resonance, a circuit behaves as a pure resistive circuit. It behaves as a pure resistive circuit. Now, so that means resonance is a condition wherein we have certain, it is basically a phenomena which occurs in the AC circuits, and at this phenomena, the AC circuit behaves in a particular uh, manner, right? So that is basically the thing which is explained here. So this is about the introduction of the resonance, right? Now resonance occurs in the AC circuits, which are either series RLC AC circuits, or they are parallel RLC AC circuits. So in both we have the concept of resonance, and resonance is basically used to in the selective AC circuits, wherein the circuits have to interact with the signals of certain frequency. So there the resonance is generally used. For example, in your radios, in televisions, when you tune the channel, so at that point of time, while tuning a particular channel, you reach to a particular value of the frequency wherein you get the clear audio or video signals. So that means at that particular frequency, you get the maximum output of the audio or video signals. So it is one basic example of resonance. Generally, resonance is used in the circuits wherein we are using the signals of various frequencies, and just to discriminate between the signals of different frequencies, we use resonance. Now, as far as your admittance is concerned, now if we see this particular thing, like here, if you see, have an AC circuit, this may be maybe series or parallel, doesn't matter, right? So if Z is equal to R plus JX, because Z is the complex number. So, and we have the admittance also, which is given by G plus JB, where B is known as susceptance, right? Now, at resonance, X and B basically the effect of X and B is null. So, Z is equal to R and Y is equal to G. Now, when we say that the effect is null, now we have to remember one thing, that at resonance, only the effect of reactance X. So reactance may be, it may be either inductive or capacitive or both. So only the effect of reactance is 0. Now, so it doesn't mean mean that the value of XL and XC is 0, right? So that means the inductor or capacitor will be present in the circuit, that is the inductor and capacitor are present in the circuit, but their effect is 0 at resonance. Now, when their effect is 0, so our circuit will behave as a pure resistive circuit. Now, this is some minor introduction about the resonance in AC circuit. And AC circuit as shown below. So we have a circuitry here in which we have a resistance, an inductor, and a capacitor connected in series with one another across an AC source. So in this, we have this R, L, and C. So let us say that capital V is the RMS value of the voltage and capital I is the RMS value of the current. And V is equal to Vm sine theta. Now this is an RLC series circuit, and in this we will have some voltage drop across each element. So it is VR, then we have VL, then we have VC, right? VR, VL, and VC. Now we'll write the parameters here. V is the RMS voltage, and this is the supply voltage. I is the RMS supply current, and VR, VL, and VC are the RMS voltages across R, L, and C respectively. Now, we need to understand one thing about the resonance in series uh, RLC circuit, that because in series circuits the current is same, uh, and voltage is distributed across each element, that is R, L, and C. So we at times may refer the resonance in series circuits as the voltage resonance. Now, however, it is series resonance. Now, let us come back to the concept. Now, VR is basically I into R, VL is actually I into XL, and VC is equal to I into XC. Now these two are, no, we know that XL is the inductive reactance and XC is the capacitive reactance. So the net reactance in the circuit is X is equal to XL minus XC. So this would be the net reactance. Now the total impedance is Z is equal to, because Z is a complex quantity, it is given by R plus J X, or it is equal to R plus J XL minus XC. So the magnitude is under root R square plus XL minus XC square. Now let us mark this as some equation number 1. So there may be 3 cases in this for the net reactance. If we take the net reactance for XL minus XC, 3 cases are considered. The first case is XL minus XC is greater than 0, means XL is greater than XC. Then what will happen? Second is XL minus XC is less than 0, that is XL is less than XC. What will happen in this case? 3, when XL is equal to XC, or you can say XL minus XC is 0. So this is the condition when net reactance is 0. Now this can also be understood with the help of a diagram. So if we draw the diagram here, frequency versus reactance, and this is the frequency which is measured in hertz, and reactance is measured in ohm. Now we know that this XL is nothing but 2 pi FL, and XC is nothing but 1 upon 2 pi FC. If L and C are constants, then XL is directly proportional to F and XC is inversely proportional to F. So let us draw these two cases. So this is your XL, and then we have the another one. Let us take XC. So XC would be something like this. So this is your XC. Now they would intersect at one point. If you can see, they are intersecting at this particular point, right? So at this particular point, their value is equal. The value at this point is XL is equal to XC, right? So this, what is this? Frequency value. That means at some point of frequency, value of F, XL is equal to XC. This is one way basically. Now we call this as some frequency which we will discuss later on. Now As we have mentioned here in this case that there are three things. If XL is greater than XC, now what will happen to the given circuit? How will the given circuit behave? So this is the question now. If XL is greater than XC, so in this condition, your circuit will behave as an inductive circuit. If XL is less than XC, then your circuit will behave as a capacitive circuit. Now, if XL is equal to XC, so let us see what happens. So if you put this condition in this equation number 1, so you will get Z is equal to under root R square plus 0, or Z is equal to R. So that means your circuit is behaving as a resistive circuit. So now if you relate this condition Z is equal to R with the condition here, this is what we were discussing, that at resonance, because the power factor is unity and power factor is also given by the equation R by Z. So at resonance, Z is equal to R, which means that your circuit is behaving as a pure resistive circuit. So that means when XL is equal to XC, as it is mentioned here, Z is equal to R. So at XL is equal to XC, or XL minus XC is equal to 0, Z is equal to R, which means when XL is equal to XC, the given RLC series AC circuit will behave as a pure resistive circuit. Now we can relate this with the condition of condition of resonance. So we can say that at XL is equal to XC, resonance is obtained in series RLC AC circuits. So now from here we have got one more definition of resonance for series RLC circuits. So we can say that for series RLC AC circuits, resonance is the condition, because if we are saying that the resonance is obtained when XL is equal to XC, so we can say this it in reverse also, that resonance is the condition at which the inductive reactance XL is equal to the capacitive reactance XC. So this is one condition, and the given circuit is a pure resistive circuit. So this is one thing, right? Now, okay. So this is one definition for the resonance in series RLC AC circuits, and because our XL is equal to XC, now this is the condition here. So if we say that let at resonance XL is equal to XL naught and XC is equal to XC naught, then XL naught is equal to XC naught. Now, if you multiply this with the current basically, or right, I here and I here, for example, and let us take I naught instead of I, where I naught is the current at resonance. So this would be VL naught. Now you can come to this one. We know that VL is IXL and VC is IXC in general. So I naught XL naught will be VL naught is equal to VC naught, or VL naught minus VC naught is equal to 0. Now what does it mean? Now, so this means from here you can say that the effect of voltages across the reactive components is 0. The effect is 0, not the voltage is 0. They will have the voltages, but since they are cancelling each other, so we are saying that their effect is 0, right? So we can say in this that in a series AC circuit which is of RLC type, the XL and XC cancel each other's effect. Now, this is what happens in series RLC AC circuits. So also your the total voltage V will be equal to PR. This is the total voltage, because we know if we see here this voltage V is actually equal to, if we can write it somewhere, like we'll write it here, V is equal to, so it is VR plus J VL minus VC, right? So if we put VL minus VC is equal to 0, like here, right? So we will get V is equal to VR. Now let us talk about the phasor diagram at resonance. So for this, we need to go back to the circuit. So let us come here. So we know that in resistance, the current I and the voltage VR are in phase. In inductor, the voltage VL leads the current I by 90 degrees. And we also know that in capacitor, VC, the voltage across capacitor lags the current by 90 degrees. So if you have observed one thing, and that is the current phasor will remain the reference phasor. It is on the horizontal axis. So we will take that only. So let us take the current phasor as the reference phasor. So this is I. Now let us draw the voltage phasors. Now VR and I are in same phase. Now VL leads the current I by 90 degrees, and similarly your VC lags the current by 90 degrees. So this would be the phasor here. Now instead of writing it as VL, VC and VR, we will mention it as VL naught, because we are taking the parameters at resonance, I naught, VC naught and VR. Right? So either you can mention VR or you can mention VR naught. That is a different thing, because this is just to distinguish between the normal values and the values at the resonance. So this is it. This is the only purpose of showing this notation and nothing else. Now let us come back to this one. Now we were discussing here and we said that at some value of this frequency, we have an intersection point between the capacitive reactance and the inductive reactance, right? So that means if we divide this part into two, so everything here we have the inductive, and everything here, not everything, basically we are talking about the AC circuits, right? It is now capacitive. Okay, it is capacitive here. So what do we call this value of frequency? This frequency is known as F naught, or we can say it is FR. This we call as the resonant frequency, right? This we call as the resonant frequency. Now here in this, if you have observed one thing, that here here in this area, your F is less than FR, and here it is F is greater than FR. So now from these two formulas, you can make out if the frequency reduces, XC will increase. Okay, so F increases, XL also increases. If F decreases, XL also decreases, and XC here will decrease, but here XC will increase, right? So this is how you can understand. So if XC increases, so we have the second case. If XL increases, we have the first case. And at this F naught, this one, we have the third case, which we say as the resonance condition in AC circuits. So that means the resonance occurs at a frequency known as the resonant frequency, right? It would be denoted by F naught, or it may also be denoted as FR, one same thing. Now, how will we derive the expression for this resonant frequency? That is the question now. The equation for the FR or F naught is derived as, now how will we derive? We know that at resonance, XL naught is equal to XC naught, and XL naught is equal to 2 pi F naught L, and XC naught is equal to 1 upon 2 pi F naught C. Now we can put these two. Now let us take these two equations and substitute it like here. So we have 2 pi F naught L is equal to 1 upon 2 pi F naught C. Now if you rearrange these two, you will get 4 pi F naught squared is equal to 1 upon L C. So we have F naught square is equal to 1 upon 4 pi L C. So we have F naught is equal to 1 upon under root 4 pi, so it is square here, 4 pi square L C. So then F naught is equal to 1 upon 2 pi under root L C. So this is the equation for resonant frequency, right? So F naught depends upon value of L and C, right? So how will we obtain the resonance in series RLC circuit? So we can say in series RLC, so this is a separate thing here. And this is a separate thing, right? In series RLC AC circuits, resonance is obtained either, the first case is by keeping L and C constant and vary the value of frequency f, or the second thing is by keeping f constant and vary the value of L or C or both, right? So from this we have observed this particular thing, that the resonance can be obtained in this way. So to summarize, we have the resonance in AC circuits wherein the voltage and current are in same phase, right? And the resistance is the impedance of the circuit is equal to resistance. The power factor of the circuit is unity, right? And the inductive reactance and capacitive reactance will cancel each other at resonance. Now, we can also understand that how some parameters vary with frequency in AC circuits. Now, this is a question mark. So let us understand this with the help of a diagram. So let us draw the variation of certain important parameters of AC circuit with the frequency. Now this is, let us say 0. This is your F naught or FR. Now the first thing is the impedance. So let us divide this in two parts, right? Here F is less than F naught. Here F is greater than F naught. As far as impedance is concerned, impedance will reduce to minimum and then will increase. So at resonance, the impedance is minimum. Z is equal to R. This is R, right? So we'll write here at resonance, Z is equal to R, or you can say that Z is minimum. It is minimum. Now, what about the current? Now, let us draw the current also. Because your impedance is reducing and current is equal to V by Z. So, if Z is reducing, so current will increase. So, it will increase in this way, reach to a maximum value, and then will decrease. So, this is the current. And this is a Z impedance. So you can see here that the current is maximum, right? So it is I naught. At resonance, the current is maximum. At resonance, the impedance is minimum. So I is maximum. Maximum. Right? Now what about the power factor? Now let us draw the power factor also. So the power factor will be, now it would be something like this. Like this. So here at resonance, the power factor is 1 cos phi. So this is power factor cos phi, right? So here the power factor is leading and here the power factor is lagging. Now why is it so? For this you need to see this diagram, because the frequency for which the value of frequency is greater than the resonant frequency, your circuit is behaving as an inductive circuit, and for the frequency less than the resonant frequency, your circuit is behaving as the capacitive circuit. So here also, if the value of frequency is less than resonant frequency, because the circuit is behaving as the capacitive circuit, so the power factor will lead. And here for the frequency greater than resonant frequency, the circuit is behaving as the inductive circuit, so power factor will lag. Now, this was all about the series RLC circuit resonance condition. Now we will proceed to the resonance in parallel RLC. Now let us come to the resonance in parallel circuit. Now in this, when we have to understand the resonance condition, so we take the example of a practical uh, tank circuit. So a practical tank circuit is shown here. So we have that a tank circuit is one in which a coil and a capacitor are connected in parallel to each other. So let us consider this circuit. We have an AC source. We have a coil. So coil is generally, or you can say we have a solenoid. We can also call it as solenoid, and a capacitor are connected in parallel. So this is what a tank circuit is. Now, let us mark the parameters. Capital V is the RMS value of voltage. Capital I is the RMS current. V is equal to Vm sin theta is the input voltage. R is the resistance. L is the inductance here. And C is the capacitance. So the current in this would be equal to, let us say, IL. And here the current is IC. Now, the resonance in this will also, see, the condition for resonance is same. Now in this, when the current in both the branches is equal, because here the current is divided, voltage remains same. So if we have to draw the phasor diagram here, so as far as the phasor diagram is concerned, the voltage phasor is taken as the reference phasor V, and then we have the current phasor, which is this one, let us say. So in this we will not take it like this. So let us remove this one. Now V is the reference phasor, and we know that the voltage across this coil or solenoid is V and the current is IL. So we know that because this is an inductive circuit and not a pure inductive circuit, so we will say that the current will lag, this IL will lag the voltage by some angle phi, and let us say it is L, for example. L is to indicate that it is for inductive circuit. And when this current IC will flow in this capacitor, and this capacitor is also having the same voltage across it, which is V, because this is a parallel circuit. So we will draw its phasor, which is like this. Because we know that in a capacitor, the current leads the voltage by 90 degrees, right? So this is 90 degrees. So this is the phasor diagram of this particular circuit diagram. Now let us find out the admittance of this particular circuit. Now as far as the admittance is concerned, because in our previous lectures also we have understood that in parallel AC circuits we prefer to use the admittance instead of the impedance. The admittance of given circuit is because there are two branches here. Okay, so the admittance of this would be J omega C, the susceptance basically, and for this we have R plus J omega L. So this is the impedance of this one. This is the impedance of this particular circuit. So YC is equal to 1 upon ZC and 1 upon J omega C, sorry, 1 upon J omega C. and this is YL is equal to 1 upon ZL. So the net impedance is admittance is Y is equal to J omega C plus 1 upon R plus J omega L. And this is obtained because we know that Y is equal to 1 upon Z, and Z is, if we take the impedance of that, so we have 1 upon Z is equal to 1 upon ZL plus 1 upon ZC. So by putting the equations here, we will get this one. So 1 upon Z is nothing but Y, and 1 upon ZL is R plus J omega L, right? This one. And 1 upon ZC is equal to 1 upon 1 by J omega C. So this will go up. So we have this equation here, right? Now, we can simplify this one. So Y is equal to, we can factorize this. So J omega C plus 1 by R plus J omega L into R minus J omega L divided by R minus J omega L. So Y is equal to J omega C plus R minus J omega L divided by R square plus omega square L square. Now we can rearrange this equation. So we will get Y is equal to the real part, and the imaginary part we will separate. R square plus omega square L square plus, now J omega, and then we have C minus L by R square plus omega square L square. Now, this is the admittance of the given circuit. Now let us mark this as equation number 1. Now, at resonance, now in this, if you see, this is the real part and this is the imaginary part, right? Now in parallel, basically AC circuits at resonance in parallel AC circuits, specifically the tank circuit, the imaginary part is 0 and omega is equal to omega naught. So omega is measured in radians per second. Okay. So if we do in that way, so we will put this as 0. So let us put it equal to 0 and see what happens. So C minus L by R square plus omega square L square, and then we have this J omega, it is equal to 0. Now this will be 0. So we have C minus L by R square plus omega naught. This is omega naught now. Omega naught square L square is equal to 0. Now on solving this equation, we have got R square plus omega naught square L square is equal to L by C. Or we can say that omega naught square L square is equal to L by C minus R square, and this is plus sign. So from here we have omega naught square is equal to 1 upon LC minus R square by L square, and then we have, or omega naught is equal to under root 1 by LC minus R square by L square. So now this is the equation number 2, and this is the expression for the resonant frequency in parallel AC circuit. and this is for tank circuit basically. Now, because omega naught is equal to 2 pi f naught, so equation 2 can be written as 2 pi f naught is equal to under root 1 by L C minus R square by L square, or f naught. Now this is measured in radians per second, right? And this is measured in hertz. Now in this is, let us say, equation number 3. Now in equation 3, if you see, if R is small, then R square by L square is very less than 1 by LC. So we can neglect R square by L square in equation 2 or 3. So under this condition, the resonant frequency is omega naught is equal to 1 upon LC under root, because this part will be 0 neglected, or f naught, so this is radians per second, f naught is equal to 1 upon 2 pi under root LC hertz. So as you can see, this is similar to the resonant frequency of a series RLC AC circuit. So from this we have understood one thing, that uh, in parallel AC circuits, it is something wherein what actually is happening, if you see these two parameters, when you talk about the tank circuit. So tank circuits, what they do, because we know that when they are connected to some AC source, so this is L, this is C basically. So they interchange their energies, the stored energy. So when this condition is achieved, we call it is resonance in tank circuits. So this is all about the lecture, and thank you so much.